Everybody, so welcome to the 2025 Walker Cisler Lecture. I'll just give a quick introduction to the lecture itself. So, the Walker Cisler Lecture is dedicated to the improvement of science education and is generously supported by the Hawley Foundation in Cisler's memory. Well known for his leadership of the Detroit Edison Company, now DTE, from 1954 to 1971, Walker Cisler enjoyed a career marked by a lifetime of personal, professional, civic, and business accomplishments. As an international ambassador for the American electric utility industry, he worked closely with heads of state both at home and abroad. A tireless and dedicated humanitarian, he strove to improve the quality of life for people everywhere. For example, through his efforts in rebuilding the electric grid across Europe after World War II. The Cisler Lecture was established in his honor at LTU in 1995 with the mission of making science education accessible to all. And with that, I turn the microphone over to Dr. Bruce Pell, who will introduce today's Cisler Lecture speaker.
Okay. All right. Good afternoon, everyone. It is my tremendous pleasure today to introduce today's Cisler Lecture speaker, Dr. Jane Heffernan. Dr. Heffernan is a full professor in the Department of Mathematics and Statistics at York University in Canada, where she holds the prestigious York Research Chair in Modeling Infection and Immunity, and also serves as co-director of the Center for Disease Modeling. She is currently serving as president of the Society for Mathematical Biology, the largest organization for mathematical biologists in North America, and also sits on the board of directors of the Canadian Applied and Industrial Mathematics Society. Her research centers on developing mathematical models to better understand how infectious diseases spread, evolve, and persist. By integrating mathematics and epidemiology and data science, Dr. Heffernan builds sophisticated models that help us understand disease burden and inform responses under a variety of conditions. Her work has offered critical insights into how immunity develops and wanes after infection or vaccination, with major implications for vaccination strategies, therapeutic interventions, and public health policy. To date, she has authored over 150 publications on diseases such as COVID-19, influenza, HIV, tuberculosis, and measles. Dr. Heffernan's impact reaches far beyond academia. She's a dedicated science communicator and a frequent presence in media and public outreach. Whether speaking with students, appearing on radio and TV, or leading workshops, she brings energy and clarity to complex topics, often with creative twists involving zombies, vampires, and werewolves, to make her points accessible and fun. Please join me in warmly welcoming Dr. Jane Heffernan.
Thank you, Bruce and Matt, for the introductions, and thank you everyone for coming, and thank you so much for inviting me. I've really enjoyed my time here today and meeting everybody, chatting, and getting the nice campus tour. So before I start talking about the work that I do, I thought I'd give a little bit of history about how I came into being a mathematical biologist or disease modeler. So when I was in school, I always liked math. I also always thought about becoming someone that would be able to work in medicine. And I have always loved to travel, and I've also always loved to look at architecture, like buildings, but mostly looking at floor plans. And so when I was in high school, I went to my guidance counselor, and I asked her, I have a long line of teachers in my family. And so I said to my guidance counselor, I've always liked math. What can I do with math other than teach? And she said that I could be a pilot or an architect. She didn't even mention engineering. And so I thought that was interesting. And I wasn't I also told her I was interested in travel and things like that, and I wasn't that interested in becoming a pilot or an architect, though I love to look at floor plans. And so I decided to go to university to become a math teacher. So I went to a small liberal arts college just kind of northeast of Toronto called Trent University. And at the time, Trent had about 5,000 students. So similar size to Lawrence. And there I was in a education program. So while I was getting my undergrad, I was also getting my Bachelor of Education. And so I decided to become a math and computer science teacher because that would guarantee me to get a job in a good school or in a good school board. And in my final year of my undergrad, I took a course, I was in applied math, I took a course called Mathematical Modeling. And we used this textbook called Mathematical Models in Biology. And this book is written by a professor at the University of British Columbia called Leah Cachette. And this book and that course totally changed my life. That's when I found out, I was also minoring in physics, and so I knew that math could be applied in physics, and I knew that math was important in computer science. I was doing a lot of work in that area, but I didn't know that math could be applied in biology. And so this is the course that changed my life. And at the time, my boyfriend, who's currently is now my husband, he was also planning on going to grad school, and so he also helped encourage me to think of going into graduate school and pursuing higher education in applied math. And so that's where I really decided that I wanted to use math to study health in applied math, but mostly focus on the mathematical modeling component. And because when you're going into this area, into academia, you get to travel. I've been all over the world, and I get to look at really cool buildings in every city that I go to. And so this is where, when I'm talking to high school students, elementary school students, I try to talk to them about how math and biology are intimately linked. Because a lot of students that you even talk to now who go into biology, they're like, oh, I wanted to do science and I went into biology because I don't like math. But math is integral in biology. And so what is mathematical biology? So it's mathematics and biology together, and we use techniques and tools of applied math in my lab to look at practical applications: biology, kinesiology, chemistry, health, medicine, biotech. And for example, I work in disease modeling. There are lots of applied mathematicians that work in climate change, image processing, medicine and public health, like bioinformatics, protein structure, vaccine discovery and development, psychology and looking at social behavior and modeling that with game theory, and also ecology. So I work a little bit on honeybees as well. And endangered species and bird migration. And to just give you a bit of context, the conference in the Society for Mathematical Biology that I go to every year, and I'm currently the president of the society, there have been some really cool presentations, even to looking at the optimization of a golf swing to get that swing to get in the direction that you want it to get to with different types of clubs. We've also looked at the optimal swing in terms of the kinetics of the body to look at ensuring that you get the sweet spot of the bat in baseball. And so there's some really cool presentations that I've got to listen to. And of course, I'm really interested in the ones that look at medicine and health. So prior to COVID, people would ask me what I do. And I would say, well, I'm a mathematical modeler. And some people thought that meant that I walked down a runway modeling mathematics. And so we'd have lots of discussions, and usually I would end up with, oh, well, I didn't like math, or I wasn't good at math. But during COVID, there was a lot of, I don't know what happened here, but in Canada, there were mathematical modelers that were informing government strategies. And so every day, the models were talked about in the news. And so When people heard that I was a mathematical modeler, I then became somewhat of a celebrity in my small circles, and I was on the radio and on TV and things like that. And so this is just a small snippet of different articles that were published in different media sources globally about mathematicians and mathematical modelers in COVID that kind of brought my field open into the public more. And so some of the questions that I would get during COVID, and even prior to COVID when I would talk to people about my work, it's like, what's in a model? What do you do? What do you look for? What data do you use? What mathematical tools do you use? Are models right? And if a model is wrong, what does that mean? And so the answers to these questions really depend on what problems you're working on. So what's in a model? It depends on how refined the question is. What do you do? I make models, I analyze them using mathematical tools, and I use computer simulations. What do I look for? A lot of people think that math is quantitative, and so we will look at quantitative results, but often we're looking at the qualitative outcomes as well, because of shifts in things, so that we can look for when those shifts are happening. What data do you use? Sometimes I don't use any data. Sometimes I use data, and I have to go through lots of hoops to get access to data. Data is of different quality too, and so when you're using data, sometimes it brings in a lot more work into a project to try to not massage the data, but to change how the data is formatted so that it's in a usable format. The mathematical tools that I use most often are calculus and algebra, some probability, some statistics, but mostly I use systems of differential equations, which are built off of calculus. And the last two questions are, models are wrong, but some are useful. And I'm going to try to show you some of the useful outcomes of the models that we work on that can help inform public health and medicine. So after I finished my undergrad, I did finish my teaching degree, and then I went on to a master's program at Western University in London, Ontario, and I looked at genetic evolution, I modeled genetic evolution in bacteria. And then I did my PhD in modeling T-cell and virus dynamics in HIV patients, and just looking at the natural fluctuations and whether we could try to understand natural fluctuations in chronic infected HIV patients mathematically. So I became really interested in immunity when I was working on that. And so after my PhD, and Dean Nelson was my external examiner for my PhD. After my PhD, I moved to England and studied mathematical modeling of immunity and waning immunity at the University of Warwick in Coventry. And this is where I became really interested in this feedback loop between the individual and the population. So when you think of immunity, everyone has their own immune system, and everyone's immune system is different. So when you are exposed to an infection, your immune system works and determines whether you're going to get infected or not. And if you do get infected, how mild, moderate, or severe your infection will be. And that immune system also determines how transmissible you will be. And so when we're thinking about infection and immunity, we think about this in immunology, in mathematical immunology as well. And so it's an individual characteristic. But when we think about vaccination and infectious diseases, we also all naturally think about the public health outcomes that go with that. So it's also, infection and immunity are also population characteristics. And so when we have a population of individuals, we have some population distribution of immunity. We also have a population distribution of infection. And we look at waves of infection and how they move through the population. And so we come to this feedback loop where individuals are feeding into the population maybe some infectiousness to other people, But at the population level, the prevalence of an infectious disease is determining what diseases you will become exposed to as an individual. So we need to think about these things. Also, in terms of immunity, you have a population level of immunity that we try to get to help the population be protected from an infection. So we think about herd immunity. But the herd immunity is a sum of all of the individual immunities. And so we have this feedback loop that we need to be thinking about. And so when we work in my lab in mathematical immunity and infection, we look at in-host modeling. So we model the cells and the virus in the body or other pathogens of your immune response. And we also model vaccines and how they elicit immune responses and how they generate memory in your body or immunity. So when we're looking at in-host modeling, we also try to discern the level of severity of your symptoms that you will experience. And one of the reasons why we do that is because at the population level, that's going to change your behavior. You're going to stay home, which means effectively your transmissibility into the rest of the population is lower. So we need to think about that. So I look at vaccination as well. When we're looking at behavior in the population, we have to think about behavior uptake and waning of behavior, the same way immunity can be gained and wane over time. So we look at how individuals make decisions based on the level of infection around them, social media messaging that they're looking at with their social media groups, as well as their family leniences or tendencies, so things like that. We also look at how, what the public health messaging is. In Ontario during COVID, it was to stand a hockey stick apart. That could be 2 meters apart. In Europe, I moved to Europe for a year during the pandemic, and there it was 1 meter apart. So we were looking at this different messaging and why messaging is different in different places. During COVID, I also did a lot of work for Health Canada to look at healthcare demand modeling. And some of that modeling can be used to look at PPE procurement. So how many masks and gowns and visors do we need to the government to have in all the different provinces so that we can ensure that our healthcare workers are going to be optimally protected. So when you think about infectious disease spread too, people do think about how infectious diseases can be spread over transportation networks. And so we have colleagues that look at the risk of importation of infectious diseases. But when you're thinking about importation or traveling of infectiousness across the world too, in my lab, we also look at a lot at how immunity is traveling around the world. And so an interesting statistic is that I think it's like 70% of people who live in Toronto are either they've immigrated to Toronto or they're children of immigrants. And in that, there's different vaccination and infection histories that come into Toronto. And what we have found in our studies of immigration to the Toronto area is that our level of immigration is effectively boosting the distribution of immunity in Toronto. But that distribution or that boost can be different in different cities. Like in Regina, in Saskatchewan, that would be a very different immigration profile than in Toronto. So we would have to look at those to be different. Okay. So I'm really interested in looking at waning immunity and how things get boosted in immunity as well. And so here you can think of, this is your first experience where you're challenged by a pathogen. And this is the profile that you usually will take, where in your immunity, you get some activation of your antibodies and your T cells, and it's around here where your symptoms are most severe, because the symptoms are really showing you how active your immune response is. And then when the virus or pathogen starts to be controlled is when you'll see this decay in the effective immune response, And then at this time, you'll see this increase in your immunity, and that can be your antibodies, your long-lived B cells, your long-lived T memory cells as well. And so those memory cells, antibodies, can last a long time in your body, and it's different for different pathogens. And then this means that when you're exposed to the pathogen a little bit later, you can have an inapparent or reinfection if you get infected. So you could have an asymptomatic infection, but hopefully you're protected against infection. And then even years later, you could also have a mild or inapparent reinfection. And so what we're interested in looking at is 4 different types of pathogens and vaccination profiles. You can think about this in terms of looking at a conveyor belt, where you get infected, and say you get infected here, and you get this big increase in immunity. And then your immunity will decay down the conveyor belt over time, and the rate of the decay of the conveyor belt, or the rate at which it's moving, depends on which pathogen you're looking at. So for measles, this is very slow, okay, and almost inapparent movement. But for influenza, your effective immunity can decay quite quickly, because the pathogen is evolving away from the immunity that you have. It can also, for pertussis, for whooping cough, this decay can be quite quick. That's why we have so many vaccines in the vaccination schedule for pertussis. And in COVID, this is also quite quick. And so you can think about, these are your infections, and you can get boosted depending on where you are on the conveyor belt. The boost could be small or big. And then the yellow here is your vaccine. So you can get a vaccine, it can boost you up to here, and then it can decay down to here, and then get boosted back up when you get another dose. And so we're interested in looking at over your lifetime. So over a year, over many years, over your lifetime, what your immunity profile is going to look like for different infectious diseases. And so before I get started talking about some of the work that I'm doing, I thought it'd be important to give you some history based on what kind of motivated me to be in this field of mathematical modeling in health. And so this is Daniel Bernoulli, and he is an example. So he's one of the Bernoulli family. There are many Bernoullis. They're all very famous. And this is a bar graph of smallpox cases in, I can't see where it is, but anyway. This is one of the first examples of using a graph to educate people in the community, in the city, to go get vaccinated. And this is for smallpox. This is an area of London called Soho, and this is a project looking at cholera. And so this is back in the early 1800s, and Jon Snow, not the guy from Game of Thrones, but Jon Snow, a scientist, mapped out the different cholera cases in Soho and used center of mass calculation to figure out where likely the water source is that these people were using that was affecting their, providing them with contaminated water that increased their risk of cholera. And so using this in public health, then he was actually able to lobby the government to cap the well that people were going to, and that's when the number of cholera cases drastically reduced. This is Ignaz Philipp Semmelweis, and he is called the savior of mothers. So for a while, he was the director of this hospital in Vienna, and he was perplexed by 2 of the obstetrics wards that were in his hospital. One of the obstetrics wards was run by doctors, and one was run by midwives. And at the time, the obstetrics ward that was run by doctors had a higher incidence of a disease called puerperal fever. And even so, like these obstetrics wards were open on opposite days, so every other day. And it was so bad in the one ward that people who lived in Vienna, if the women were going into labor on a day that they knew that they'd be going to this obstetrics ward, they would choose to instead have their baby on the street. And that's because they would have their baby on the street so that they would be eligible for public health care. If they were at home, they wouldn't get it. And so this was very perplexing to Semmelweis. And so he used a statistical analysis of looking, and remember at the time, doctors were men and midwives were women. And so he went through an analysis of the daily orders and duties of the doctors and found that the doctors were studying the biology inside of bodies right before they were going to the obstetrics ward. And so they had their hands in cadavers. And this is predating the germ theory. And so he realized that maybe there's something on their hands. And so he put in a rule that doctors would have to wash their hands before they go to the obstetrics ward, and the level of puerperal fever went down. This is Ronald Ross. He's well known for his studies on malaria, and he's one of the first examples of using some mathematical and statistical models to look at the outcomes of malaria in terms of looking at control of mosquitoes and contact between humans and mosquitoes. And he won a Nobel Prize for his work. And this is Kermack and McKendrick, and these are the fathers of disease modeling and what it is today. So they developed this mathematical model called the susceptible, infected, recovered, or removed model. And it's based on a system of 3 differential equations that look at how people transition from susceptible. A susceptible can come into contact with an infected person, and that then moves them from S to I, and they spend some average length of time in the I class, which is 1 over gamma. Gamma is the rate of removal out of the I class to the R class. And then the people can be in this R class, which is for removed or recovered. And so here's a graph of a basic SIR model here down on the bottom right. And so you can see that this is a limited model in the population. So we have a certain size of population. Some of the people will get infected, and that depends on how many, depends on the parameter values that we use. And then you can see that they transition through the infection, and effectively it moves people from susceptible to removed. And so what we use in disease modeling here is that people are 100% susceptible if they're in the S class. And if they're in the removed class, they have either died or they're 100% immune. So they can't be infected again. And so the assumptions in this model are very restrictive, but you can build a lot of things off of this model. And that is what the entire field of mathematical epidemiology builds off of this model into more complex scenarios. And we'll look at a couple of those today. This is, so I've looked at, that's mathematical epidemiology. This is the amazing model that started mathematical immunology. And so this was co-founded independently by these 2 researchers, Alan Perelson and Martin Novak. And here you can see a similar type of model. So here we have target cells. Those are noted by T. And then we have pathogen, which is noted by V. And the first model was for HIV. So this is a virus. The virus particles come into contact with the target cells and they infect them. And those target cells then move to the I class, at which time they become infectious target cells, which means that they make new virus particles. And so this is the simplest model in, just like the SIR model, this is the TIV model, and this is the simplest model that we build all of mathematical immunology off of. So if we go back to the population level, remember we looked at the SIR model before, what if we want to now include an E class, for people who are infected but aren't infectious yet? So we want to incorporate that. What if people become vaccinated? Well, we'll move people from the susceptible class to the vaccinated class. The people who are vaccinated and infected, see in the recovered class, they can move to this W class. That's for waning immunity. Maybe they have some partial susceptibility when their immunity has waned. And so they can have an exposure and an infection that is so mild that we don't even know, but effectively gives them a boost in their immunity. So some things that we want to think about. We can also put in hospitalization, treatment classes in here. We can also, from the I class, they can go to R, which is recovery. That's for an acute infection, where you can clear it and you can become recovered. But if you go to C, that is a chronic infection, and then you can move, you are existing in that chronic infection for forever until maybe you get treatment and you can recover. So that's something like hepatitis C or B. You can get something like that, or tuberculosis, something like that. So, but there are a billion things that we can build onto this. The asterisks or the stars are things like where you can subdivide these classes into many things. You can think that you could have this model for different age groups. You could have this model for different populations, and the populations are connected by networks. You could have this model for different immunity statuses. Like if you are in the S class and you have a higher level of antibodies than I do, then maybe you'll get a mild infection. You'll go through your own SEIR model, and I'll go through my own SEIR model. And that's where we have that in-host modeling, that individual model, now embedded into the population level models. And so one of the questions that we have in Math Epi is how many levels of distinction do we need to be able to capture most of what people in the population are experiencing? And so that's one of the current questions that we're looking at in my group. So we also saw the basic model of mathematical immunology, which is TIV. And here I've now, that model had no immune response in it. It was embedded inside the parameters. But now we can have target cells, infected cells, and pathogen or antigen it's called here. But we can now incorporate B cells and T cells and antibodies and different kinds of B cells like naive and memory cells, and T cells naive and memory and effector. And we can look at CD4 T cells. They're the helper cells. They help activate the rest of your immune system. So the CD8 T cells, when they're activated, they go and they kill infected cells. The B cells, when they mature, they produce antibodies, and those antibodies go and neutralize virus or pathogen in the body. And so there are all these different aspects that we need to think about when we're looking at modeling. Now, this doesn't even include all the other things in the immune response, like interleukins, interferon, different aspects of the immune response and the network of the immune response. And so this is where we come to, our models can be huge, but when we have huge models in immunology and epidemiology, we incorporate a lot of uncertainty because we can't measure everything. And so the larger your model gets, the more it can replicate. But you have more and more uncertainty in the model, so you're not so sure about the results you're getting. So we look at an optimization problem every time we have a research question. We have to think about how big and how small do we need our models to be to answer the question and to reduce the uncertainty that we're getting so that when we get results, they're actually meaningful and we're learning something from them. Okay. So I'm going to look at an example of some work that we did during COVID-19. And I'll give you a little bit of background on COVID-19 in Canada, and then I'll look at the model that we've used. Well, I'll look at it in the Ontario context, which is where I'm from. But just so you know, we're also applying this model to California, New York, Hungary, England, France, and different provinces and territories in Canada. Okay, and if people want to use it to apply to other countries, just contact me or other geographic regions, and I'm happy to share the model because it's freely accessible. Okay, so this is COVID-19 in Canada, and I'm from Ontario, which had the most cases. Well, actually, yeah, the most cases. And what was interesting about COVID in Canada is that every province and territory more or less got to decide what their public health restrictions would be. And in Ontario, we had one of the strictest public health situations. And so this is data. So I'm going to use data from all of the infections in Ontario, and I do have a Canadian context model as well that I won't talk about today. We also looked at vaccine uptake and by age, because our model is going to be delineated by age over time. And so we look at first dose, second dose, third dose, fourth dose. And so the level of doses makes the model more and more complex. So we have to think about how we want to average all those doses into, say, maybe one or two categories so that we can simplify the math in the simulation. We also, during COVID, the public health situations changed over time. So we had students in my lab going through news reports, announcements from public health and government in all the geographic regions and more that we're looking at to determine what the restrictions are every week of the pandemic so that we could incorporate these public health restrictions into our models. Because when we're looking at the spread of disease in a population, we have to look at what the average number of contacts are per day that's related to transmissibility. And so if we have work from home or school closures, these are going to affect different age groups differently. And so we have to incorporate into our models things called contact matrices. And these matrices are delineated by age. I'll show them in a sec. And those matrices are going to change depending on what the restrictions are. And so this is an example of some things that we have on GitHub. It's kind of similar to the Oxford Stringency Index, but ours is based on 4 categories, which align with population mixing matrices that are developed for every country in the world. And so you can see Ontario is really strict. It's almost always red. These are different times during the pandemic. And then there's a lot more flexibility in the green in different locations. So over time, too, we have to incorporate how the virus is changing. And so every time there's a new variant of concern arriving in the geographic location, we have to then change the risk of infection. So we have to recalibrate our model depending on what is reported for that variant of concern called the reproduction number. And so we look at all the different variants of concern over time, and this is something that we have to calibrate our model to. Even different strains of Omicron we have to consider. So when we're looking at the public health context and the epidemiology, there's the public health restrictions that are being enforced or messaging related to the population, but we also then have to consider the compliance to the restrictions. And like I said before, we have increases in compliance, and then people's behavior will just naturally decay. Whether it goes back to baseline like pre-COVID or some other baseline, that depends, and we're working with some social scientists to see if we can understand that. But we need to try to capture that too into our model. And so there are lots of things, there's lots of uncertainty into the model that we had to address using sensitivity analysis. And so I'll talk a little bit about that. So one of the first things that we did is we looked at in-host modeling, and we tried to understand when you're given clinical trial data for the vaccine or infection data from infection studies, how we can use a similar mathematical model to look at infection and immunity separately. We also we needed to calibrate our model with the reproduction number. And so this is, at the beginning of a pandemic, there's always a race for mathematical modelers like me to determine what the reproduction number is, the basic reproduction number, because this gives us our baseline of infectiousness. And so it's defined as the number of secondary infections produced by an initial infective when introduced into a totally susceptible population. And so here you can think of it, I'm the index case, and I've had, over my infectious period, I've had contact with all of these mathematicians that are at York University or in the Centre for Disease Modeling in Canada. And I infected Dr. Jankowski and Dr. Wu. And so my basic reproduction number is 2. And so that means that I'm only one person, and I've replaced myself with 2 people. So if everyone increases their infection with more than one individual, then the infectious disease is going to grow. Okay. If it's just replaced by one individual, you'll see some persistence in the population. Deterministically, it'll be a flat line. Stochastic, maybe with stochasticity, it will decay to 0. But if it's less than 1, then the disease dies out. And when we look at the SIR model, there were 2 parameters. There was beta, which was infection, and gamma, which was the rate of recovery. And this reproduction number is equal to beta over gamma. And so we can then, using beta and gamma, we can say, okay, well, if we decrease infectiousness, then we'll decrease the reproduction number. If we limit the infectious period, we'll also decrease the reproduction number. But how can we do these things? Through public health interventions, social distancing, having social bubbles, work from home, school closures in dire situations. Give people vaccines because we're decreasing in susceptibility, so we're removing people out of the susceptible class. We can give people drug therapy during their infection that will decrease their infectiousness, because we're also decreasing their infectious period. There are so many things that we can do to affect these parameters. And with the larger models, we can look at all the different contact tracing rates, hospitalization rates. We're using PPE effectively, all these different things. And so early in the pandemic, I was talking to my kids, and we were talking about how fast COVID can spread. And so on the far right here, I was looking at a model that's parameterized for COVID on a social network. So the lines, the green dots here are susceptible individuals, red dots are infected, and the invisible dots are people who have recovered. And so you can see that in this right, on the left, that's your left, right? Yeah. And so you can see the disease spread really quickly through the population. And so that's if we have no public health restrictions. On the far right, all I've done there is I've kept the number of contacts per individual, but now I've made it more cliquey. So so it's almost like social bubbles. So people have 8 contacts still, but they don't really have very many contacts outside of their cliques. And so you can see that COVID will spread slower in that population, but it will still spread. And so you'll eventually get some spread. And so that's like our social distancing or social distancing bubbles that we had during COVID. In the middle, what I've done is I've taken the cliquey model and I've reduced the contacts by half. So instead of 8, now I have 4. And with that cliquey and social distancing bubble, and reduction of contacts, which has some public health, like work from home or school closure, you can see that the infectious disease really can be staved off, that maybe there's an importation of the disease into the population, and so on. And so this is something that I use to look at what different public health contexts. We can do a lot of other different things with this simple model, but just looking at the basis of social distancing and cliquiness can really help stave off infection and look at that reproduction number. So I didn't incorporate vaccination in there, but we can. And you can think, so over here on the left, we have individuals who are susceptible in blue. The green are infected but can't infect anybody else yet. Orange are infectious, and the red are people who are immune. And if we now remove people with vaccination, you get the thing on the right. That's the same population, but now the people who are vaccinated are invisible. And so effectively what you see with vaccination is that it's stopping chains of transmission, or effectively increasing the distance between susceptibles. And so when we look at this in the math epi context, we think about the distance that vaccination can provide you in terms of an infection. Over COVID, I worked a lot on hospital demand modeling. Every week I wrote a report for Health Canada to look at what our demand was going to be for ward beds and ICU beds in different geographic regions across Canada. And if people are interested, I can talk a little bit about that more later. So I just wanted to give a little bit of an idea of what an in-host model could look like. So on the right-hand side, we have a biological model of a vector DNA virus vaccines and mRNA vaccines, so what they do biologically. On the left-hand side, we have a mathematical model, so this is our flow diagram of our model, where we've had to look at, this is the larger model, is the whole model that we would love to be able to use, but we can't because we don't have enough data. So if we use that large model, we'd have a lot of uncertainty. So we had to use mathematical techniques to bring the dimension of the model down into something that's usable and also can give us some results. So what we do is we take this model of vaccine and we fit this model to actual vaccination data, which we get, which includes antibodies and maybe an interleukin, like of an IL-6, and the data could also maybe include interferon gamma. And we can fit this model to vaccination data, and it can give us an idea of what the other parameters in the model should be. We do the same thing with infection. So on the right-hand side, those are the different steps that COVID takes when infecting a cell. On the left-hand side, we have the mathematical model of that. And so this model is more complex, but it's actually quite similar in terms of the level of uncertainty that we have. We know a lot more about infection than vaccination in some aspects. And so here, on the bottom row, we have interleukin, interferon, this thing called granzyme B that sometimes we get measurements of. And then there's also antibodies in here. And so we can use a similar model, like the vaccination model, to fit to infection data and give us some measurements of other parameters in the model that are important when maybe we're looking at the effects of drug therapy. Remember, there wasn't a drug early on in the pandemic, and then we could look at the parameters and maybe look at, if you want to design a drug, what should the drug, what components of the life cycle of the virus should the drug target, so that we get minimization of the infectiousness and severity of infection in individuals. And so here we have an example of the vaccination model that we've used to fit to 14 different data sets of vaccines. And so here we have a combination of Pfizer, Moderna, and AstraZeneca. And so these are data from studies that are published in the literature. And so we took the data, we fit our mathematical model, and we're able to get a population level fit, which is if all of them are the same, that's the orange curve, what that looks like on average. And the blue curve are the individual fits of each of the data sets. And when we do a similar thing for infection and vaccination, we can get some things that look like this. So on the left-hand side, I have some outputs from work that we did. The top two plots are on AstraZeneca vaccine, where we're looking at the 2 doses and spreading the 2 doses out further apart, or even halving or quartering the second dose, and what that would mean for our T-cell immunity and our antibodies. And on the bottom plot here, we're looking at specific studies that looked at Pfizer and Moderna. And in all of these cases, we're interested in looking at what the immunity decay is going to be over time. Because if we understand the decay rate, then we know when people are going to be susceptible again, and that's when the booster dose, the 3rd dose, should be provided. And so when we were doing this work here on the left-hand side, there was a specific recommendation we were only separating these doses in Pfizer and Moderna by 21 or 28 days. So this work doesn't apply to Canada because we separated our doses by much longer time frames. But in the United States, this work is applicable. And so we found that by day 180, I believe, people should be provided opportunity to get a 3rd dose of vaccine. And while we were looking at this work, the CDC changed their policy from a longer time frame to a time frame that aligns with what we were doing. And so that was great for us to hear that other people were getting the same result, which increased certainty in our outcomes. On the right-hand side, we have our fit of our infections to infection data. So in this plot, this subplot here, I guess, which has the colorful bars above it, Those are looking at infections at different time scales of the pathogen. So we're looking at wild type, alpha, beta, and so on. And some of the time scales of the studies are longer and some are shorter. And so the fits are underneath that. And then in the top row and the right-hand column, we're looking at a study that was done in Canada where they had individuals that had mild, moderate, and severe infections. And we were trying to understand what the immune system signature is for people that have different outcomes of infection. And so if we're looking at, on the top left, we have interferon. You can see that the peaks of the blue, of the green, orange, and black, the peaks are different. The mild infection has a lower peak versus the moderate versus the severe. But the decay rates don't look terribly different except for the severe infection. In the middle, we're looking at interleukin 2, and on the right, we're looking at granzyme B. And you can see in granzyme B, the peak is the same, but the decay rates are different. In the middle, you can see different peaks and just slightly different decay rates for a couple of them. And so this allows us then to look at mild, moderate, and severe infections and how their characteristics are different at the population level. So this brings us to, remember that SEIR chronic WV model? So we developed this model to look at COVID infection spread at the population level, and it takes into account the in-host aspects. And so in the top we have our mild infections, our moderate infections, our severe infections, and the level of immunity that they gain is going to depend on the severity of infection. So if you have a severe infection, you get a lot of immunity if you survive it. A moderate infection gets a smaller level, and a mild infection gets this level. And then so these are totally susceptible. These have some immunity, more immunity, and these individuals are totally resistant to infection. And so as immunity wanes, people can be re-exposed and reinfected. And so people who are in this class have a small probability of being infected, and they can go to a moderate or severe infection. If they go to a mild infection, they just come back into this category. Here they can have a mild, moderate, or severe infection, and so on. So we're interested in tracking this. And this is different by age. So we have this done by 5-year age groups, all the way up to age 80. And the probabilities of mild, moderate, and severe infection depend on the comorbidity statuses in each age group. And we have data on that from a publication for every country in the world. And so when we're looking at age groups, we also have to take into consideration their contact structure. And I'll talk about that in a sec. On the bottom part of this graph, when vaccination was introduced, that complicated the model a ton. So we now had not just one vaccine, we had 2. Then we had booster doses, and we needed to be thinking about how immune are people if they get 1 dose from these different categories, or 2 doses, or booster doses. And then we wanted to start tracking how much infection is in the vaccinated population versus in the unvaccinated. And that was important when we're looking at the first wave of Omicron that was predominantly unvaccinated, and the second wave of Omicron was predominantly vaccinated people. Okay, so here's a graph of contact structure. And you can see here that individuals that are on, so we have age by age, and you can see individuals have most of the contact with people of a similar age as them. That's down the diagonal. And then children have contact with their parents, and these are mixing matrices for Canada. In some other countries or geographic regions, even within Canada, you might see a little bit more contact between children and their grandparents. Okay, and so phase 0 is total lockdown. Phase 1 is some public health restrictions are lifted. Phase 3 is where we reopen schools, and no mitigation is pre-COVID. In all of these graphs, when we average over the average number of contacts per day, we get this thing on the right. And you can see that no matter what kind of restrictions we're living in, the 15 to 19-year-olds have the most contacts. And so we use this information to look at vaccination priorities. And so when we're modeling the vaccine, we provided the vaccine to the elderly and the healthcare workers in our model, but we also showed that the earlier you can vaccinate the 15 to 19-year-olds, the better, because they indirectly protect the rest of the population because of their contact structure. Okay, so quickly, getting into some of the epi, this is how we calibrate our model. So here's some infection data. We're calibrating the model for looking at severe, moderate, and mild infections. And when we use that, we can look at, so here red is totally susceptible, blue is the next level of immunity, yellow is the next, and the green are totally protected from infection. And so we were asked in 2021, what's going to happen in the fall? And so what we did is we saw, okay, so in the lighter colors, these are shaded by age, you see that gray circle? That means that we're going to get a lot of infection in the 12 to 29-year-olds, but it's going to be asymptomatic mostly. And so one of our pieces of feedback was that we need to get more vaccination into those age groups. Down in the blue, the yellow, you can see that there's increases. Those increases are from infections, and so we're going to have an increase in infection, but you can see that the green is not really going up. And that's because the number of infections is not dominating the number of people who are waning out of those classes. And so, but when we look on the right-hand side, these are now color-coded by age, we can see that of the severe infections, 50% of the infections are in the age 50 plus. And so we recommended that a booster dose be provided to those age groups, individuals of those ages, if they want to go get a booster dose, because this would really reduce the level of demand on our healthcare system. We also see, when we're looking at severe infection, that 50%, most of severe infections are going to come from the total susceptible class. Not very many people are vaccinated that get infected. This is pre-Omicron. And so we really were providing guidance to try to find people who were unvaccinated to look at severe infection outcomes. When we look at different scenarios, we can also use our models to project what's going to happen. And you can see different projections here on what actually happens. So the purple shading is our projection, and we only use data up to a certain point, and then we look to see what projections go along with the data after that. And we use models like this to feed into our healthcare demand model so that we can look, if we only have a certain capacity of ward and ICU beds, how many people are being turned away from hospital when they need it? When do we need to increase the number of beds that we have in our hospitals to be available? And how long is our length of stay changing? So in the summers, our length of stay would be longer than in the winter, and that's because there's less demand in the summer, so people are able to stay longer. It didn't mean that they were more sick. So we had to take these aspects into consideration. And the last thing that I was going to say about our COVID work is that right now we're using our large model to look at a retrospective analysis, and we're looking at, so S1 is what we experienced in Ontario, so this is looking at Ontario. And what if we had no public health measures or vaccination? So that's the S2. S3 is, what if we had no vaccination, but we kept all the public health measures? And so we're looking at these bar graphs as the total number of infection incidents and the total hospital admissions over time to see how effective were our public health and medical measures in stopping a certain number of infections from happening. Which translate effectively into death. And so we're looking at that right now, looking at this retrospective analysis where we're calibrating our model with different assumptions. So that goes to that sensitivity analysis that I talked about. The bigger the model, the more sensitivity analysis we need. And so the different colored bars here are for different levels of our calibration. The purple is a retrospective analysis that the Canadian government did on all of Canada. And you can see here that these purple bars, when they are available to be compared to output that we get, that the blue bar is very close to the purple bar. And so we can get some confidence in some of our results by looking at that. So finally, I'll just say that this is COVID-19 work. I work on a lot of different infectious diseases: influenza, HIV, TB, measles, pertussis. Measles is important right now. HPV, herpes simplex virus, malaria, HCV, so on. We look at public health, vaccination, booster dose programs. We also do some modeling of in-host of rats and ferrets and so on that are in the vaccine discovery pipeline. So if we get data of vaccination in some of these test subjects, before it even goes to clinical trial in humans, can we help with our mathematical models reduce down what needs to be looked at in the next trial in the animals that will hopefully translate into optimal immunity for the population at a reduced cost, because we can shorten the length of time that it takes for a new vaccine or a new drug to be discovered and developed. We look at social and physical distancing, work from home, the behavior change. You can embed game theory into these models that help individuals make decisions. And so we're working with some social scientists on that. We work with a lot of different people: government, pharmaceutical industry, educators, and so on. Our modeling is funded and supported by a lot of different entities. So those are our funding bodies there. And the work that I've shown today was done by a lot of different people and in collaboration with a lot of people as well. And so if you're interested, you can have a look at what we're doing in the literature. And I'm also happy to take some questions if there's time.
All right, thank you very much, Jane. So I'll just open things up to questions, and I'll run around.
Thank you. Thank you very much. It was really, really nice and illuminating. My question is, if you can go one slide back. Another one, yeah. So if I understand correctly, the S1 is what happened and S2 is what would happen without measures. So recently I traveled in different countries in meeting any sort of people. And what I noticed, that myself, I'm actually embarrassed to talk about how much I believe in the preventions measures in terms of vaccines, social distancing, because the 90% of people that I meet, they don't believe at all in all these measures. And this is kind of incredible to me as a scientist. I'm a psychologist. So my question to you is, what can we do as scientists to have a better contact with the general population, because whatever we are doing is really not working?
Yeah, so I think the harder the restrictions, the more pushback there are on them. And so one of the conversations that we had a lot in Canada and in France, because I was there for a year as well, was trying to understand what the limit is that people will easily adhere to. And so how long does your isolation need to be? Does it need to be 14 days? Could it be 10 days, and how much would that affect it? And so I found that the more restrictions there are, the easier it is for people to uptake the restriction for a short period of time and then change their behavior, not back to what it was before, but to have it wane. One of the things that we have in one of the associations that I work in is the Canadian Immunization Research Network, and there's a social science pillar of that network that really tries to look at how people change their behavior in related to vaccination. They're also trying to work with people in education and social science to look at messaging. We know, like when we're looking at social media or our phones, our news feeds, the advertisements change, and there's an optimal half-life of an advertisement for clickbait. And so maybe our public health messaging also needs to have this type of optimal half-life of a message, so that it's there and then they change the method or the message. And so that's something that with the social scientists, I think that there can be a lot more in psychology discussion about is what, when you're looking, like, I don't know, so some of the data on this next slide, so this is some work that we did on changing behavior, and this graph here is looking at how immune people become to messaging about Hurricane Katrina. And so in the beginning with Hurricane Katrina, people were very, acknowledging it, and it was important, and there's a lot of resources that would have to go in to help people. And then after a while, you start to ignore the news messaging, even if it's still there. And the surface area of the news in newspapers and radio surface area and TV and so on decreases. And so what do we need? What kind of change in the messaging do we need to excite people back up to pay attention to something? And so you can think about it in terms of the sensitivity of your nose. There's a bad smell and you get used to it. How bad does the smell need to be for you to smell it again? And so that's a good question, something that I've been thinking about for a while. But this is the rate at which people decay their behavior back.
All right, thank you.
Thank you very much for the talk. I have to admit I don't know a whole lot about mathematical modeling, but I was looking at some of your models with like the SEIR and all the various states in the model. I was trying to get an understanding for the complexity of the individual nodes in that model. Is that just a variable? Is that some sort of Gaussian function? What level of complexity is that, or what level of complexity does the data actually support?
Yeah, so these are variables. And so here I have 4, 8, 12, another 12, and another 8. So I have that many variables by age, by 5-year age groups. And the arrows are parameters, and some of those parameters can include an interaction. And so some of these, like an S, when it moves to an E, is because it's come into contact with someone who's in the E's and the I's. No, only in the I's, actually.
Is that a probabilistic transition from S1 to E1?
It incorporates probability, and so the transmission parameter is a combination of contact structure and probability of transmitting the pathogen with an infectious dose. So we also have to look at the quanta that are being expelled in the in-host model.
Thank you.
Any other questions?
Thank you. So I'm wondering about the long-term effect of COVID in the population. So like one story that was in the media is, COVID will turn into the common cold. And one issue with that is that there's, mutation over time, and, it's always a little bit confusing how much last year's vaccine is going to apply to the next year. So does your research kind of tell us about what we should expect, even if we are diligently getting vaccines every year? Should we expect our vulnerability to kind of maintain relatively constant, or what should we expect?
So we do some work on trying to track evolution of COVID over time. We do for flu as well, because this helps you determine what vaccine, especially for flu, what vaccine should be developed for that flu season. And it's 6 months ahead of time for flu. COVID doesn't evolve as fast as flu as far as I know, but I'm not an expert in the comparison. But for COVID, there's been a big drop in vaccine uptake. And that's because people are tired of it, in part. but also because when they do have it now, it's very similar or even milder than a cold. It's a coronavirus, and so its mild infection is like the common cold that's also a coronavirus. And so people are trying to think of this more like influenza, but I think we need the pandemic to be a little bit further away for some people to start thinking more and more about yearly vaccination. It's offered, but just people aren't going to get it, but they're going to get the flu vaccine. So they could get both when they're at the pharmacy. So the long end of it is I don't really know how to go about it, but we are researching it. We're also researching hybrid immunity because there's so many different vaccines available for COVID and with different technologies. And with the infection, my history of infection and vaccination is different than your history of infection and vaccination. And so how do we understand that? My husband is a biochemist, and he looks at the affinity between how strong proteins bind in vaccine discovery and drug discovery. And so anytime a new vaccine came out during COVID, when we were eligible to go get it, we went and got it because we wanted to experience the new technology. But I don't know if we were, like, what that really means in terms of my hybrid immunity and yours. But there's a lot of immunology data in Canada that is available for study for this with the COVID Immunity Task Force. And so we're trying to get an understanding with some preliminary models with one of my PhD students right now.
Again, thank you for your talk. I'm not quite sure how to ask this question. It's a little different context. You know, when COVID started and first took off, the response was fairly dramatic in terms of applying lockdowns and closed and distancing and all these sorts of things. And over the years, they discovered that probably was not the right way. I look back at the Great Barrington Declaration, for example, Bhattacharya's work that they did, and their predictions that were ignored. I'm wondering how you can use your model to ask the question, had they done what the Great Barrington people suggested, what would have happened to the disease distribution, the kinds of things that you've seen happen over time, and your modeling based on what really did happen? Could you have suggested what would have happened had they actually done what Bhattacharya and his group had recommended?
So I don't know the recommendations that you're referencing, so I'd be interested to know more about that. But this is one thing that we're doing with this retrospective analysis, is to see what public health mitigation strategies were really effective and which ones weren't needed. And so this is over a summation of a couple of years, but we're gonna look at different time frames. And one of the big interesting questions for me and for a lot of people is school closure. Did we need, in Ontario, we had online learning for a long time. And did we need as much of that? And so this is one of the things that we want to look at. But in terms of the beginning of the pandemic, there was so much uncertainty. That's why, so there's a protocol that's called First Few Hundred. And so this protocol is at the very beginning of an outbreak. You follow the first few hundred infections very closely. You do their contact tracing. You can take virus measurements, immune system measurements, and so on for the first few hundred. And if you follow them very closely, you get a lot of information quickly. And so certain countries in the world have these protocols. And so the information that was coming out of like the UK was really important. And so daily we had administrators in the Canadian government combing all of the news articles, the publications, the things posted in all the archives, combing things so that we, the modelers, could get parameters and things that we could calibrate our models to. And so in Canada, we don't have one of these protocols, and I think we should. But I'm a mathematician. I need to convince some other people to get that. But in Australia and in the UK, and I can't remember where else, important information comes out. But Australia was quite limited this time because there wasn't a lot of infection. The UK, a lot of information came out. But we still have so much uncertainty. And so the more certainty we could get sooner, the less restrictions we're going to have.
Thank you. Other question? Oh, yes.
Thank you. Right. Thank you, Jane, for the wonderful talk. Right. So one question I was thinking of, pandemic happened many times in human history, such as the Black Death and the Spanish flu, and then SARS and COVID. It always happens so quickly and spread out, and it's just like hopeless, and eventually all disappeared. So do we understand how every single time eventually disappeared? What was the reason, or what we could do to, it's not just like a social distancing or something like that, but even different kinds, right, different natures. So yeah, could you answer that? Thank you.
So in terms of disappearance, I don't think that they totally disappear. They decrease. And so like the 1918 influenza pandemic, we still have influenza. And some of what we see in circulation now has bits related to the 1918 pandemic. But in terms of if you look for it, you can find it. There's a researcher that just got the Gairdner Award in Toronto, and for data mining infectious diseases. And so very much, if you look for something, you can find it. And if you don't look for it, then you think that it's not around. But there can be infections that are just asymptomatic. Like think about influenza, where you have the seasons. We think that it just comes and goes every winter. There must be some influenza that's happening over the summer. It's just that maybe the infections are very mild, or the climate is quite different. There's a couple of infections maybe. Is it really that the virus is migrating up and down like the birds? Like we need to think about these aspects. And so it's perplexing, these seasons and climate, and how we can capture those patterns. And trying to understand how immune responses could even be different given the outside temperature. But some diseases have disappeared, but the only one that has really disappeared is smallpox. And trying to understand why it did. It's touted that the vaccination campaign really got rid of it. But I think there was also some environmental conditions that helped optimize the probability that it would go away. And so we need to figure out that for all the infectious diseases.
I don't always need a mic. Thank you again. Presentation is amazing, and I'm actually very familiar with your research, so it's a wonderful and honor to have you here. I was wondering if you could speak maybe to the fact that a lot of, I did Ebola response, I worked with COVID, the fact that the numbers we have on infection and disease tend to be actually very skewed, and we're finding this out now with COVID, with people who would say, I'd get a call from, the person who was like monitoring me, and I would just give them whatever answer I could so I could get out of the house. Or in Liberia, people would lie and say, no, I have malaria. And then we'd find out later from testing, but also the tests were inaccurate. How do these models kind of deal with that? And then too, on the Spanish flu, it's actually the Nebraskan flu. The research shows actually probably came out of America, but thank you.
So this relates to how restrictive the policies are, but also it relates to the economics of the person. And so how much do they need to leave home to make money so that they can get food and so on. So there's that too. There's also mistrust in government. And so these things are all really hard. So I just went to a workshop in Banff, how many months ago? Like 8 months ago? And it's specifically where we had mathematical modelers that model behavior, and social scientists who have surveys to try to understand behavior change. And right now we're writing an article together on, you have this behavior model called Megaflu, and you have this social science survey called Flu 5000. So 5,000 participants, they have all these questions, and we very much work independently right now, but how can we come together to really understand why some of these things are happening and how we can mathematically try to project with more certainty what our curves are going to look like 2 weeks from now, or a month from now, or 6 months from now. And right now, a lot of projections only work for 2 weeks. It's kind of like the weather. Like there's short-term forecasting and long-term forecasting. And this is why all models are wrong, because when you make a model, it depends on certain things of the current day, and then part of the reason why they're wrong is because you release the results, you've informed the government puts in restrictions, and now what your model showed is never realized. So you don't even know what the probability is that it will be realized at all either.
That exactly happened with Ebola. Every single week we had a new mandate. It was just too far behind. That's wonderful that you found that.
Yeah. Any other questions? So I have one. I saw you divided things up between the level of severity of the COVID. Was that, I'm sort of curious with the data, was that usually as we get COVID, we didn't like get a test and like go, then, I'll check a box 1, 2, or 3 for my severity level or something like that. Was that post-infection like survey data, or was there like a proxy for that, like hospitalizations, ICU entries, or where did that data come from?
So you mean the infection data?
Yeah.
Okay. So I just wanted to say first that this structure where I had severe, mild, moderate, and severe infections, this model we made in the first week of COVID when everything, the lockdown was. I was like, what am I going to do with my time? I work on waning immunity. Let's make a model. So the dotted line and up, I made with colleagues, and it was just chance that we got these we just put these 3 categories, like we're thinking about the common cold and things that we know about waning immunity, and a lot of the parameters that we guessed about on back of the envelope calculations ended up being right, which was really insane. But the data, the infection data here, this is data from immunology studies. And the ones at the top and the right, they're with a collaborator at the University of Toronto, where they were specifically funded to look at outcomes of infection in mild, moderate, and severe cases. And this is funded by the Canadian Immunization Research Network and COVID Immunity Task Force. And I was a scientific advisor to the CITF over COVID. And so early on, I got to see a lot of this data and then see if we could calibrate our models to that. But there are different types of infections that people were looking at and interested in by age and by ethnicity as well as job, because there were workers that we needed to be working every day. There's the healthcare workers and so on. So we're trying to understand things. But we are also trying to understand the difference between sexes. And a lot of the differences that we did find in the waning immunity didn't involve sex at all. So the waning immunity by sex wasn't important, but the age was. And so most of this is just data that was received because of funding. If we didn't have funding, we wouldn't know any of this stuff.
Okay, thank you. Any other questions? All right, so I invite everybody to thank Jane again for a wonderful talk.
Thank you.